Hey, what's up, guys? This is Chung here again. So this time, LeetCode number 629, K inverse pairs array. Okay, so we're given like integer arrays, nums, and then we define an inverse pair. So the inverse pair is a pair of integer where the index I is smaller than j, but the value of index I is greater than j, right? And then you're given like two integers and a k. Okay, you need to return the number of different array consists of numbers from 1 to n, right? Such that there are exactly k inverse pairs. Okay, and since the answer can be huge, do a modular with this 10 to the power of 9 plus 7. All right, so some examples, right? So we have n equals to 3 at k is 0. In this case, we only have 1 to n, right? So in this case, we need 0 inverse pair. So obviously this one, the answer is just 1 because with 0 inverse pair, which it means everything needs to be sorted from the smallest to the biggest. That's why the only valid array in this case is 1, 2, 3. Right? Now with this one, right? So now if we have one pair, the answer is 2 because we could have two possible permutations of this 1 to n numbers. So one is 1, 1, 3, 2, right? 1, 3, 2. So here this is one pair, right? Or we could have 2, 1, 3. It means this is one pair, right? So 3 to 1 is not one of it's not the answer because 3 to 1 has or 3, 1, 2 is not 3, 1, 2 is not the answer because 3, 1, 2 has two pairs, this one and this one, and we only need one, right? So the constraint is 1000, right? Okay, cool. So I mean, for this kind of problem, I mean, a brute force way is what? Since we have 1 to n, right? A brute force or brute force means a search, right? We just brute force search all the possible permutations, right? Since we're asking about the permutations of this 1 to n array, right? I mean, a brute force way we can do a permutation of all the of this array, and then we check how many pairs, how many inverse pair in that permutation. But that obviously won't work because with 1000 factorial, it will definitely TLE, right? So, and also ask us to find the total count, right? I mean, if the search doesn't work, and then we don't have a lot of options left for us, So most likely this one is going to be a DP problem, you know. Or if you still don't know DP, we can we can start trying to solve it, right? By giving an example here, right? Let's say we have. Let me think. So let's say we have five. N is equal to 5. Okay, and k. Mm, let's leave it for now. Okay, so let's say n is equal to 5. We have 1, 2, 3, 4, and 5. Right. So let's think about how can we make an inverse pair. Obviously, we need to move some larger number in to the left, right? For example, if we move 3, to here, right? Then we'll have like some inverse pairs, right? In this case, we have 2, right? Because 3, 1 and 3, 2. All right, and mm, Um, so let's think about 5, right? Let's say we have 5 here. We want to move 5 because based on the location we move 5, we could have end up having different different like inverse pair. For example, like I said, if we move 5 to here, right? So we will have like let's move 5 to here, right? So if we move 5 to here, so what we'll get? We'll have like 4 inverse pairs in this case, right? And if we move 5 to here, right, we'll have 3, right? And then so on and so forth. So here we have 2, here we have 1, right? Okay, and after that, right? So after that, what do we have? After that, we have let's say at the beginning we have n and k and n and k states here, right? And after moving this a number here, let's say 5 here, right? We will have we'll end up having some of the and after this we'll have like what? We'll have n minus 1 number left, right? Because once we move 5, 5 is out of the picture now. So we only have 4 numbers left. And out of those 4 numbers, we need to have like a different we need to form the remaining inverse pairs, right? Basically, let's say we have this one, and then it's gonna be a what? Gonna be the gonna be the n minus 1, right? So this n minus 1 based on where did we move 5, right? So this is the current state, right? So we have n minus 1. So we can move 5 to here, right? That's why we have 4. Not 4. We have k minus 4, right? Because this is gonna be the previous state, right? And then we have what? So we can also move 5 to here, right? So it's going to be n minus 1, k minus 3, right? Because by moving 5 between 1 and 2, we are creating like 3 inverse pair. So as you guys can see, though this for different options, we need to accumulate them together because since we're calculating the total the total permutations, right? Which means, because by moving 5 to here, we are creating another branch, right, of all the possible permutations. That's why we need to accumulate all the states together here, right? So here, again, we have n minus 1, right? Then k minus 2, right? Until the last one is going to be n minus 1 dot 0, right? Yeah, 0 means that, we're not moving 5 at all, right? So which means, okay, so we decide not to move 5. So which means we're not creating any reverse pair. That's why, we have, sorry, not 0, I mean k, right? Yeah, k minus 0, I'm sorry, k minus 0, which means k, right? So 4 means that, so here, so the upper bound of this one is actually it's a minimum of k and n, right? Obviously, so this one actually we're using the k minus 4 here. So lower bound it's clear that basically it's still k, but the upper bound here, first, k cannot be negative, right? That's why, when we do this subtraction here, we need to make sure this thing is not it will be greater than 0. So that's the first condition. The second condition is that, this will also depending on how many n's here, right? As you guys can see, so the maximum inverse pairs we can create given n is the n minus 1, right? Cool. Yeah. So I mean that's basically now as you guys can see, right? So now we by moving the this 5, right? Actually, we're creating some sub problems, right? After moving 5, we have sub problems which has a fewer n and has a fewer of k, right? Because that's a basic a perfect candidate of using the DP, right? Where given like this two state, we can just easily reuse the result by them, right? By the previously calculated result. So I think we already have the DP transition function, right? So we have DP of n and k, or DP I and j. Okay. So what does this one have? This one has it's going to be accumulation of the DP I minus 1 to k, right? To m. I would say m here, or j. Yeah. M here, right? Where m is from 0 to what? To minimum of I minus 1 and j, right? So that's a range of m. So we have this two, like I said, first, the yeah, because this one, we cannot make more. We cannot make more than I inverse by using the current one, and also by using the current I here, and then we also cannot make the this one negative, right? Actually, sorry, this is going to be the k. Sorry, this is j minus m. Yeah, yeah. So that's going to be the DP state transition function here, right? You know what? Let's try to do the implementation for this one first. Okay, so we have DP, right? So let's define a DP here. It's going to be a 0. We are going to be obviously going to be a two-dimensional DP, right? Range of n plus 1. Okay, and for I in range of 1 n plus 1, and then for j in range of 1 to k plus 1, right? Gonna have like an m, right? So the m in range of the like I said, it's gonna be the minimum of I minus 1 and j, right? We also do a plus 1 here, okay? And then dp ij gonna be accumulate of everything, right? So dp I minus 1 and then j minus m, right? So this is what I mean by the two conditions here. First, since we're doing subtract m here, right? So first, this one bounded to the just m means that how many creating, right? M new inverse pairs, right? So first, this one bound to the I here, because it cannot, since we have I numbers in total, we cannot make more than I minus 1 inverse, right? Because the best we can do is just to move this number, the last number, to the beginning. That's how we can create I minus 1 inverse pairs at most, right? And the second one is that, it's bounded to j, because since we're doing j minus m, so m cannot be greater than j, right? Otherwise, this one's going to be a negative, which is invalid scenario. Okay. Yeah, I think that's it, right? I mean, in the end, we simply return the dp 0 and -1 and -1, right? I think we need to fill in some base case here. So basically, we haven't, because everything starts from 1. We have to consider the base case. So the base case, let's say if I is equal to 0. So when I is equal to 0, it means, let me think. I is 0 means that there's no number at all. Okay, so I think I equals to 0 is fine, because I equals 0 means that it's 0, because it means there's no there will be no inverse pair at all, because there's no numbers at all, right? And then when j is equal to 0, so j is equal to 0 means, oh, actually it's the base case, it's the example 1 here. So whenever the k or j is equal to 0, it means that we only have one options. It's the sorted array here. That's why, okay, we can set this one here. If I in range of n plus 1, so dp I 0, it's gonna be 1, right? So that's the base case here. And yeah, I think that's the basic logic here. If I run this one, I think this one should work. Okay, accept it. If I submit, but unfortunately, this one will TLE, because remember the constraint is 1000, right? Okay, yeah. So it's 1000, and we have 3 nested for loop here, right? And this is like n cube time complexity, and that's why TLE, right? So we need to improve this one, and which is the part we can improve here is the last for loop here, because as you guys can see, we are doing like accumulation for each j here, right? For each j, we're accumulating everything for this I plus 1 from the previous I minus 1 to some with some like index here, right? But as you guys can see here, actually when we're accumulating, let's say j is equal to 4, right? We'll be accumulating something like, this is I, right? This is j. We'll be accumulating something like a j minus 1, j minus 2, and so on and so forth. But when we calculate j is equal to 4, right? We're also accumulated some of them already, right? At least for j, for I3, right? Or I2, right? I'm pretty sure those things have already been calculated, right? Being accumulated while we're calculating I when j is equal to 4. So when we accumulate, we're trying to calculate j is equal to 5, right? We're pretty sure, so we can somehow improve this part. But how? In order to do that, let's try to do some examples, right? So let's say we have dp5 5. Not Let's try to generalize this thing first, right? So we have I and j, so we have dp I minus 1 and j minus 0, right? So if we just follow this one here, right? Plus dp I minus 1 j minus 1, right? And then I'll just write this thing here, j minus 2 plus, until we are reaching the end, which is I minus 1 j minus, because the last one, so what is the last one? The last one is I minus j. Sorry, the last one is j minus I minus 1. Remember, so this is one of the condition, the condition for this one, because remember, so this is the most inverse pair we can create with given this I, right? Let's give another one before this one. Okay, it's gonna be a I minus 2, right? So this is a general general like expression for the inner for loop here, right? And I think you already seen that, right? So this one, there must be some duplicated here, right? So since it's like accumulation, so every time j's will only be increased by 1, right? So what can we do? If we replace j with j minus 1, what do we have? Right? So if we replace j with j minus 1, right? So I'm pretty sure you guys already see the idea here, right? So let me do this. It's going to be j minus 1, j minus 2, j minus 3. So here, j minus 1, this is plus 2 going to be j, this one, right? So this is going to be this one, right? So it's clear, right? So, and we have so many common items here, right? So if we use the first one to subtract the second one, right, we can eliminate most of the common part, right? I j minus 1 gonna be what? So because this part is gone, this is gone, this is gone, right? And this is gone. That's what I'm doing here. So all the diagonal word, this is anti-diagonal elements can be cancelled out, right? So the only thing left here will be this one and this one, right? So that's why we have dp I minus 1. It's going to be j, right? So minus subtract I minus 1 and then j minus I. So that's it, right? Oh, and since we're doing the dp ij here, we can move this part to the right side, right? That's why we have this one, right? That's exactly what we will get here. Cool. So I guess that's actually this is exactly what we need, right? So we can simply remove this inner part here, the inner for loop here, and then we can simply copy and paste this part to here. But we have something we need to be careful. Remember, we used to have this kind of rate condition here to make sure the second part will not be negative. So here we have already making sure this thing can satisfy this I minus 1 condition, right? But how about the j here, right? J means we use the minimum of j to make sure second part will not be negative, right? But here we are not considering that, that's why we have to add the second condition back somehow, right? That's when we need to handle this part, because here the previous two are fine because we're sure, since we're starting from 1 here, this I minus 1 j minus 1, they should be fine. But this is the part we need to be handle separately. We simply just add a like if check, right? So we only subtract this one when if the j is greater than I, right? Else 0. So that's it, right? And if I run the code again, I think this should also work. Oops. Oh, shoot. Yeah. I forgot to do the modular here. 10 to the power of 9 plus 7. Okay, and then we just do this. Cool, it works. Actually, so in Python, it's easier to do this modular in Python because when we do this kind of add and subtract in Python, it can automatically help us to scale this number. If you were to solve this problem in other language such as Java or C++, you have to do some like trick here to make sure this dpij will not overflow. But in Python, it handles it for us automatically, so we only need to do the modular in the end. But in C++ or Java, I believe maybe you need to do a modular, and then to make sure when you do a subtract, will not get the negative values. Probably you need to do a plus this mod plus this mod, and then do a something like this, right? To make sure this thing will not overflow or get like a negative value. Yeah, so now as you guys can see, so since we removed the inner for loop, we only have n squared time complexity, right? That's why this one can pass. Yep. And I think that's pretty much it is. Okay, thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.